Another type of example of a number that we care about might be a population mean. By the way, all these numbers that we care about estimating are all population numbers because we're trying to make a conclusion about the population using a sample. So this proportion of success that we've already talked about was also a population proportion of success. And so this is a population mean as the next example for a number that we care about estimating. So as an example, as a motivating example, let's say that you want to know what the average IQ is for the entire country. So one way to do it is give every single person in the country an IQ test, score the IQ test for all 300 million Americans, and then take the average of all those scores. Just punch them in your calculator, your calculator will give you an average. That's one way to do it, but what's the issue of doing it that way? Yeah, you can't feasibly get every single person to take an IQ test. So remember when we talked about trying to call every single American up and ask whether they approve of the president? We said that on average that would take about 5 minutes, and even so that would be entirely infeasible to do. In this case, taking an IQ test takes much longer than 5 minutes. It takes hours. So each person taking hours, it would be completely infeasible to have every single person taking an IQ test and then take the average of all those results. So instead, we have to look at a sample, look at what the average IQ test, average IQ score is for that sample, and then extrapolate a conclusion for the average for the entire population. And the conclusion that we get will be in the form of a confidence interval. The true IQ will lie within some interval, a certain percentage of the time, like 95% of the time. So the conclusion will also be a confidence interval. So we have a formula for the confidence interval when we're trying to estimate a mean, just like we have a formula for a confidence interval when we're trying to estimate proportion of success. So recall, previously when we're trying to estimate a proportion of success, the formula that we talked about last class was P, the population proportion of success, was equal to P hat plus or minus the z-score times the square root of P hat Q hat over N. This is the formula that we talked about last class to estimate this true population proportion of success. So now, when we're trying to estimate this new measurement, this population mean, we're going to use a different formula. So it'll be the true mean is equal to, I'll just read the symbols as is and we'll talk about what they mean, is equal to x bar plus or minus I'll do two cases here. Plus or minus z alpha over 2 times sigma over the square root of n. So let's give some concrete numbers in our example, and then we'll talk about how to apply this formula. So let's say that we're trying to estimate this very thing, which is the average IQ for the whole country. So we said it wasn't feasible to give everybody in the country an IQ test. So instead, we're going to gather a random sample. Let's say 50 people. So let's say n equals 50. So in this sample of 50 people, we give each of those 50 people an IQ test. Now it's much more manageable. And then we grade those 50 IQ tests, and then we punch the IQ scores in our calculator, the 50 IQ scores. And let's say the calculator will give us a mean and a standard deviation. So let's say the mean is 102, the standard deviation for the sample is, let's say 14. And remember, when we first started talking about standard deviation, we made a big distinction between a population standard deviation and a sample standard deviation. So when you have these 50 IQ scores and you punch them in your calculator will give you the standard deviation of this sample of 50. So it's giving you a sample standard deviation. A population standard deviation is if you were to know the IQ scores of all 300 million Americans and punch them in your calculator, then your calculator can tell you the population standard deviation of all those numbers. So in most realistic situations, we don't know this population standard deviation. But you notice that this formula for the confidence interval, the formula that I wrote up here requires a population standard deviation. And usually this is not practical, this is not feasible. But for the sake of example, let's say that we knew this population standard deviation. So let's say that this turns out to be 15, because you know that with IQ scores, we've talked about this before, the mean turns out to be 100, and the standard deviation for the population is 15. For the sample, it turns out to be 14. But let's say that we knew this. And then we'll talk about the more realistic case where we don't know the standard deviation after we talk about this. So for simplification, let's say we know sigma, the population standard deviation, so that we can use this formula. So this mu is the population mean that we're trying to find. So this is unknown right now, we're trying to find it. So to use this formula, it requires x bar, and x bar is the sample mean observed directly from the sample. So that'll be 102. This z-score is calculated exactly the same way as the z-score that we talked about in the last class. So let's leave it for last because the other numbers will be easier to plug in first. So sigma will be what? Yeah, so that's known to be 15. And again, we said that knowing this isn't very realistic, but we'll talk about the more realistic case after this. And then the square root of n. Yeah, it'll be the square root of the sample size, which is 50. And then the z-score is the same way that we calculate the z-score in the last class in order to estimate the population proportion success. So remember, this alpha is the complement of the confidence level. So the confidence level is usually given to you or chosen by you. So let's say the confidence level is 95%. And in the last class, we talked about the consequences of choosing different confidence levels. And remember, we said that if you increase the confidence level to 99% or something even higher than that, then you have more confidence in your final conclusion. But what are the consequences of that? What happens to the margin of error when you increase the confidence level? Yeah, the margin of error also increases. So that means that the final interval, where you're saying that your possible values are lying within, will also expand to make sure that the true answer is within that interval of possible values. So your margin of error will go up so that your final confidence, the width of your confidence interval also expands so that your true answer lies in there. Yeah?
Are you going to ask us to choose your confidence level for test?
Yeah, usually not. Usually this confidence level is given to you. Or in real life, when you go out and you do statistics by yourself in the future, then you'll choose this number yourself. Yeah?
So like, why don't we consider the fact that they're like negative for the z-scores, like when we're looking for them?
You mean in this particular case when you're looking for this z-score?
Yeah.
Okay, so let's do this example and we'll touch on that. So if the confidence level is 95%, then this formula requires this alpha as part of this z variable. And we said alpha was just the complement of the confidence level. So alpha ends up being 5% or 0.05. And then this z-score, now that we found alpha, is really z, alpha in this case, which is 0.05 divided by 2. So 2.5% or 5% divided by 2. So if we evaluate just the right subscript, what's 5% divided by 2?
2.5.
Yeah, 2.5%. And another way of saying 2.5% is 0.025. So what this symbol means in its entirety, this is just a definition that was made up, and we're accepting it. And what this definition means is find the z-score that has this much area to the right of it. So find the z-score that has the area to the right of it under the bell curve of 0.025. That means if you're to visualize this bell curve, we're looking for a certain z-score, which is this boundary here, that has this much shaded area under the bell curve of this value, which is 0.025. So we're looking for a z-score that has this much area to the right of it. So the way that we would find this is that we would go to the z-score table, and recall that the z-score table has a relationship between two numbers. One is the z-score itself, and one is the area to the left of that z-score under the bell curve. So if we know one, we can find the other. So if we knew this area to the left of the z-score under the bell curve, then we could use the z-score chart to find the z-score. Right now we know the area to the right. So what would the area to the left under the bell curve be? Yeah, 0.975. So now we go to the z-score chart and recall that the z-score chart has a relationship between these two numbers, z-score and the left area of that z-score under the bell curve. So right now we're trying to find the z-score, so we're going to search for all the middle numbers in the table that represent left areas. So all these numbers here are going to represent left areas, and we're going to look for the closest one to 0.975, and then find the corresponding z-score. So remember, this 0.975 represents a left area, not a z-score itself. So don't start in the first column looking for 0.975. Start in the middle of the table because it represents a left area. So what corresponding z-score? 1.96. 1.96, okay. So you should be getting 1.9 here, and then an extra 0.06 up here. So that this left area is the intersection of this 1.9 plus the 0.06, so 1.96. Okay, any questions getting that z-score? Okay, so this z-score is going to be 1.96 here. So to answer the question about why we don't use negative z-scores, the reason for that is the way this table is laid out is it's laid out with z-score and area to the left of that z-score. So this right area here of 0.025, we convert to a left area first of 0.975, and then we look for 0.975 as a left area to get a z-score of 1.96. Now, if you look for 0.025 directly in the z-score table, then the table is going to think that you mean 0.025 as a left area. But 0.025 as a left area would be over here, because 0.025 as a left area means that it's less than 50%, which is on the left side of the table. So if you search for 0.025 as a left area, then you're going to be searching on the negative z-score side of the table. And you're going to get what z-score? You're going to get negative 1.96 because this bell curve is symmetric. So you're going to see negative 1.96, but that represents a left area of 0.025, not a right area of 0.025. So you're gonna get the same answer, but it's negative. So you can, yes, you could use the negative z-score table, but if you do that, you have to be aware that the answer you get will be the negative of the correct z-score. So the table will give you a negative 1.96, but the correct answer is positive 1.96.
So we use the same thing for the first formula as well, like we do the same.
Yeah, so there's one of two ways that you can do it. You can either take this right area 0.025, convert it to a left area 0.975 first, and then use that number directly as a left area to look up the z-score to get directly 1.96. Or the second way that you can do it is you could use the 0.025 directly as a left area, but if you do that, the z-score that you get, you have to know that that z-score that you get will be the negative z-score that you actually want. So the z-score that you end up getting is negative 1.96, so that you have to negate that to get the correct z-score. So that you end up with this z-score over here up right. Any questions? Okay, so so in the end, after plugging everything in, we're gonna get this expression for the true population mean. So let's first evaluate what's after the plus or minus first. And then what have we been calling this quantity that's after the plus or minus in this company too? Yeah, the margin of error. So the margin of error is also approximated as capital E for error. So let's go ahead and calculate the margin of error first. 4.16. Okay, so that's the margin of error itself, and then now we're gonna add in the sample observation representing the sample mean, that was 102. So the true population mean is this sample mean of 102 minus 4.16 in one direction and then plus 4.16 in the other direction. So if we subtract 4.16, what's the lower bound? 99.84. 97.84. 2.
106.16.
Yep, 106.16. So what does this mean? This means that in your pursuit to try to find the true average IQ for the whole population, without having to give every single person an American IQ test, you only gave 50 people an IQ test, and from there you're able to conclude that the true average IQ score for the whole country is somewhere between 97.84 to 106.16, but that'll be true 95% of the time because your confidence level here that you used for the equation was 95%. So 95% of the time, the true population average IQ will be somewhere in this area. Any questions? Okay, so let's say that